Let's just jump right into this explainer. Today, we're exploring exactly how engineers use code and mechanics to absolutely master the unpredictable skies. It's this incredible blend of chaotic real-world physics and ultra-precise computational modeling, all working together to launch a high-powered rocket and basically force it to do exactly what you want. Think about this for a second. How do you make a high-power rocket hit in exact altitude on a windy day? This is the ultimate high-stakes scenario for the NASA student launch competition. In that kind of environment, it's not just about getting off the ground, right? It's about hitting a precise target altitude under completely unpredictable weather conditions. That is what separates the absolute winners from the rest of the pack. I mean, you could build the most powerful rocket on the planet, but if a sudden gust of wind throws off your aerodynamics, you're going to miss your target. So how do engineers actually solve for weather they can't control?
Well, let's look at Section 1, the Apogee Challenge, and define the specific goal every single team is trying to hit.
The crucial thing to understand here is that in competitions like NASA's, teams have to declare an exact apogee, somewhere between 4,000 and 6,000 feet before they even set foot on the launch pad. And the rules are unbelievably strict. The closer you get to that declared number, the more points you earn. If you overshoot it, you lose points. Undershoot it, you lose points. It's basically this massive high-speed Goldilocks problem that requires a ridiculous level of precision.
Now here is where the engineering strategy gets really, really clever. Because these teams have to declare their solid rocket motor well in advance, they can't just casually swap in a smaller engine on the launch pad if they wake up and it's a calm day. They literally have to design for the extreme. Teams must size their rocket motors to reach that target apogee under a very specific NASA and FAA worst-case scenario, which is a maximum safe wind speed constraint of 20 miles per hour. High winds mean higher aerodynamic drag. So if your rocket can hit its target while fighting a 20-mile-per-hour headwind, that means on a calm, windless day, your rocket is actually totally overpowered. It's going to overshoot. So what do? They have to figure out a way to actively hit the brakes midair.
Moving on to Section 2, Phases of Rocket Flight. To really grasp how we apply those brakes, we first need to break down the rocket's actual physical journey. The flight happens in 3 rapid-fire stages. First up, you have the powered ascent. The rocket launches with this massive, violent burst of thrust right off the launch rail. Then the engine completely burns out. This kicks off Step 2, the coasting phase. Here, the rocket essentially just floats upward, fighting gravity using nothing but its own momentum until its upward velocity hits absolute zero at the exact apogee. Finally, Step 3 is descent and recovery, where the ejection charges fire, the parachutes deploy, and the rocket methodically floats back down to Earth. Throughout all of these phases, the flight is basically a giant tug-of-war. It's a dynamic battle between the push of the motor's thrust and the pull of gravity and aerodynamic drag. While that motor is burning, thrust is totally dominating the equation. But the second that fuel is gone, drag and weight take over entirely. So to accurately predict where that apogee is going to be, engineers have to know exactly how much push and how much pull is happening at every single millisecond of the flight. Which brings us to Section 3, Simulating with MATLAB, where we get to see how engineers build a digital brain to calculate this physical battle before the rocket ever even leaves the ground. You can think of this computational model as a high-tech crystal ball. You can't just use a simple high school algebra equation to find the apogee, because the target is constantly moving. The mass of the rocket is dropping incredibly fast as that solid propellant burns off. And as the mass changes, acceleration changes, thanks to Newton's second law. As velocity changes, the drag changes. It's a lot to keep track of. But this MATLAB software crunches all of these shifting variables at lightning speed, continuously integrating the sum of forces so it can predict the exact flight path and maximum height. Now here's something really wild. Computational fluid dynamics proves that drag is not just some static, unchanging number. The aerodynamic drag coefficient actually changes drastically depending on whether the rocket motor is actively burning or completely shut off. When the motor is on, the intensely hot, high-pressure exhaust leaving the nozzle actually shifts the boundary layers of air around the base of the rocket. This creates a huge spike in drag. But once the motor cuts off, the rocket just returns to a lower standard aerodynamic profile. If your software model doesn't account for that dynamic shift, your apogee prediction is going to be completely wrong.
All right, Section 4, Controlling the Trajectory. With all the math mapped out and our simulations running, let's look at the physical hardware and see how engineers force a real-world rocket to actually obey the simulation.
Remember how we established that the rocket is intentionally overpowered for calm days? Well, the easiest way to reduce that excess performance on launch day is through passive drag control. Teams pull this off by simply swapping out modular nose cones. Based on whatever the weather data looks like that morning, they run their MATLAB model and pick a nose cone with a very specific geometry, maybe conic, elliptical, or ogive, with varying fineness ratios. A shorter, blunter nose cone is going to create more drag, passively shaving off altitude to get them closer to that target apogee. But here's the catch. Passive control has a massive limitation. The weather isn't static. Wind fluctuates mid-flight all the time. To counter this, engineers came up with this genuinely ingenious active control mechanism. What you're looking at is a 3D printed 4-gear aero braking system that lives right inside the fiberglass body tube of the rocket. During the upward ascent, it just sits perfectly flush, hidden away inside to keep the rocket as sleek and aerodynamic as possible.
But then, if the system detects the rocket is moving too fast and is definitely going to overshoot the apogee, a servomotor rotates the center gear. This action forces these 3 outer flaps to deploy right through narrow slots cut into the rocket's body. Extending these flaps instantly increases the rocket's base area. It is literally the aerodynamic equivalent of slamming on the brakes in midair.
Of course, those flaps aren't just wildly popping in and out at random. They're controlled by a remarkably sophisticated brain. There's a tiny Raspberry Pi computer on board, using live barometric altimeter data, feeding it through a precisely tuned PID controller loop in Simulink. You can kind of think of it like the smart cruise control in your car when you're driving over steep hills. It's constantly comparing the rocket's current actual altitude and velocity against the ideal mathematical path, tweaking those flaps in real time. If it's flying a bit too high, it extends the flaps out further. If a sudden headwind hits and slows the rocket down, it pulls them back in. It's this beautiful, continuous feedback loop that ensures the rocket smoothly decelerates to hit its exact target apogee without just tumbling out of the sky.
It honestly is a marvel of modern engineering, taking the raw, chaotic power of a rocket and refining it with elegant, real-time code. So it leaves us with a pretty fascinating thought. If we contain the chaotic physics of a rocket launch with real-time data and active modeling, what other unpredictable real-world systems can we master next? Keep exploring that idea, and thanks so much for joining me on this explainer.